going to explain about Prim's algorithm, Kruskals algorithm, and single source shortest path algorithm in greedy method. First of all, Prim's algorithm. A Prim's algorithm comes under a greedy algorithm used to discover the minimum span tree from a graph. Executing Prim's algorithm involves the following steps. Set up the minimum span tree using a randomly chosen vertex. Find the minimum of all edges connecting the tree to further vertices, then add it to the tree. Repeat step 2 as necessarily to obtain a minimum spanning tree. So let us consider the weighted graph. So first we need to consider a weighted graph. After that, we need to select a vertex. The next step is step 3. From this vertex, pick the shortest edge and add it. So R is the shortest edge, so we add it. Now choose the closest vertex that is not yet included in the solution. This is step 4. Step 5. Select the nearest edge. If more than one option is available, pick up one at random. So continue this process until a span tree is formed like this. This is the final span tree. In both the Prim's and Kruskals algorithm, the graph should not form a cycle. Cycle should not be formed. Now let us look at algorithm. Step 1. Choose the starting vertex as we discussed above. Repetition of steps 3 and 4 until the fringe vertex is present. Stage 3. Choose an edge with the minimum weight that connects the tree vertex and the fringe vertex. Stage 4. Include the chosen vertex and edge in the least spanning tree T. So step 5. Exit. The time complexity of Prim's algorithm is mentioned here. It is big of E log V. Prim's algorithm applications. It is used in installing electrical wiring lines and in designing the network. Now let us move to Kruskals algorithm. For a connected weighted graph, Kruskals algorithm is preferred to find the shortest spanning tree. The major goal of this particular algorithm is to encounter a subset of edges that may be utilized to visit every vertex of the graph. Firstly, we will focus on sorting all the edges and we will sort them according to their weight, low weight to high. Now we will pick the edge having the least amount of weight and associate it with the spanning tree. If the edge being added forms a cycle, it should be rejected. Keeping on adding the edges till all the vertices have been added and a minimum spanning tree has been formed. These are steps we should follow in Kruskals algorithm. Now let us see an example of Kruskals algorithm. So let us consider this spanning tree. Phase 1. Join the edge PQ having the weight 1 to the minimum spanning tree. Phase 2. Join the edge ST having the weight 2 to the minimum spanning tree. Join the weight ST. Also, point to be noted that this is not making any cycle. Okay, this is not making any cycle. Phase 3. Add the edge QR having the weight 3 to the minimum spanning tree. Add the edge QR. Phase 4. Select the edge RS having the weight 4 to the minimum spanning tree. Also, you will notice that it is not composing the cycle. It is not composing the cycle. RS. Phase 5. Now, we will select the edge PT having the weight 5. Adding this edge will form the cycle, so we will dump it. Phase 6. Pick the edge PR having the weight 7. Having the weight 7. This one. PR. Adding this edge will form the cycle, so we will also dump it. Phase 7. Pick the edge PS having the weight 10. So here we will see this PS. Okay, PS having the weight 10. So adding this edge also will form a cycle, so we will dump it. The total value of minimum spanning tree is, we will add all the weights, that is PQ plus ST plus QR plus RS, that is equal to 10. In the above tree, the number of edges now equals to number of vertices minus 1. Okay. In this way, we will find the minimum cost spanning tree using the Kruskals algorithm. Now let us look at the algorithm. There are 5 steps. Construct a forest F with each vertex of the graph representing a distinct tree. Make a subset E that holds all of the graph's edges. Steps 4 and 5 should be repeated until E is not vacant. Extract an edge from E with the least weight. Add the edge generated in phase 4 to forest F if it joins 2 different trees. These are the algorithm steps. And the step 6 is for mixing 2 trees in a solitary tree, else. dump the specific edge. Phase 6, phase 9, finish. Now let us see the applications of Kruskals algorithm. The technique by Kruskal can be used to build out electrical wiring across cities. It is possible to operate it to set up LAN connections. The complexity of Kruskals algorithm is given. The ring complexity is given here. Now let us see the single source shortest path algorithm in greedy. In the context of BD method, Dijkstra's algorithm is the most commonly used approach to solve the single source shortest path problem for graphs with non-negative edge weights. It finds the shortest path from a given source vertex to all other vertices in a weighted, directed, or non-directed graph. So Dijkstra's algorithm for non-negative weights, let us see. Dijkstra's algorithm is a greedy algorithm that works efficiently when all the edge weights are non-negative. It calculates the shortest distance from source node to all other nodes in the graph. Steps of Dijkstra's algorithm. A graph represented as g of v comma e, where v is a set of vertices and e is a set of edges. A source vertex S. So the goal is to find the shortest path from the source vertex S to all other vertices in the graph. This is the main aim or goal. So algorithm steps, greedy approach. Initialize distances. Set the distance from the source vertex S to itself as 0. Set the distance to all other vertices as infinity. Create a priority queue, min heap, to store vertices based on their current shortest distance. Mark all vertices unvisited. Create a set of unvisited vertices. Extract the vertex with minimum distance. Pick the vertex u with the minimum distance from the priority queue. Mark it as visited. Now, step 4, relaxation. For each unvisited neighbor v of u, calculate the tentative distance. This is the formula. If the distance to v can be minimized, update it and insert v into the priority queue with the new distance. Step 5. Repeat steps 3 and 4 until all vertices are processed. When all vertices have been visited, the algorithm terminates. This is the graph we have taken as example. This is the table showing current vertex processed, distance updates, and priority queue, min heap. Shortest paths from A to B with the distance of 1, from A to C with the distance of 4, A to D with the distance of 3. These are the shortest paths. The time complexity of this algorithm using min heap, using simple arrays. Using min heap, big O of b plus e to log b. Using simple arrays, big O of b2, b square. The applications of Dijkstra's algorithm are network routing, finding the shortest path in communication networks. Thank you.